welcome to my talk on embedding vectors. Again, it's great to see so many here. It's really good to come back to these conferences and have so many people in the audience and not sit in front of a computer anymore and record YouTube videos. Okay, so today it's supposed to be about embedding vectors. Just a heads up, if you're very good at math and totally into embedding vectors, I just warn you, this is an introduction to embedding vectors. So if it's a bit too boring or something, feel free to leave. For all the rest, I will say this at the end again. Please give me feedback on this talk. It's very much appreciated if I hit your sweet spot. Right? Was it fast enough? Was it too slow? Did you have takeaways? Also criticism, feel free. It's very important for us to improve these talks. Okay. So who am I? My name is Christoph. I'm from Divisio, my own AI company. We are from Cologne. Feel free to contact on LinkedIn. I really like this on the conferences, actually meeting real people and connect via LinkedIn. Maybe drop me a quick line that you're not a recruiter or want to sell me outsourcing. That would be nice because I might otherwise accidentally reject your contact. Okay. Also, if you have a question about the talk, something you didn't understand, feel free to drop me a message later on LinkedIn and I will see that I can get back to you. Okay. The term embedding, there are many different words for it. Now, if you're a stickler, you will say these terms are not the same, but technically they are. So you will hear many of these terms: an embedding vector, a latent vector, a feature vector, an activation vector, a fingerprint, and these things actually are all the same. So depending on context, where you get them from, how you use them, where you are talking about it, you might use one term or the other, but everything I say now applies to all these terms. So if you ever wondered what a latent vector is, congratulations, you're in a talk about an introduction to latent vectors. Okay, so a quick reminder, we probably have, most of us have heard it, so, but just as a refresher, what is a vector? As a programmer, especially in Python, PyTorch, it's just an array of floats, right? One-dimensional array of floats. When you do deep learning, you would rather call it a tensor of rank 1. And mathematicians, well, they don't need to be reminded, but to be technically correct, which of course we want to be, it's an element of a vector space, for example, R4. And yeah, a vector is an element of a vector space. Okay, a tensor or an array. We don't need many of these mathematical details here. You can just think of it as a row or a column of numbers. That's enough. Okay, the vector dimension. This is something like, especially in sci-fi, the high dimensional stuff, okay? It's simply the length, the number of elements. There's nothing fancy to it. Like if it's a 1,000-dimensional vector space, sounds nice, just means we have more numbers, right? There are infinite vector spaces. Our vector spaces we discuss here are always finite, and the dimension doesn't change. So if you're working with one type of embedding, your dimension will be fixed. You won't change the dimension. And those high dimensions are not esoteric or anything. It's just a technical term, how many elements you have. You will often find D or N, like as an abbreviation for the number. And when you work with embeddings, it's usually somewhere between 256 and 8,192, roughly. So there are a bit bigger ones, sometimes there are smaller ones, but this is the size that you probably will work with. So the whole idea of an embedding vector is that you can actually encode knowledge in numbers, which doesn't only sound pretty cool, it is pretty cool. And if you think about that, neural networks generally, okay, there are exceptions, TensorFlow graphs with strings and etc. But normally we work with numbers, mostly floats. So it's numbers in, numbers out. That's all there is. And it's supposed to do tasks, knowledge tasks. So obviously we somehow have to encode knowledge in numbers. And this is what an embedding or a latent vector is. It's knowledge as numbers. For those with a philosophical background, it's very interesting if you know about Pythagoreanism. Okay, that's hard in English. Which is an ancient school of thought that basically the whole world it consists of numbers. Numbers have a deeper meaning. Ratios of numbers hold truth. And yeah, that was a philosophical school in ancient Greece, and it's very funny that we actually now have a provable way to encode knowledge in numbers. It's kind of nice. I think those guys, and they would have loved it. The cool thing is, because we now have vectors and we can do math with vectors, that means we can do math on meaning, which is still cool. I mean, I'm pretty used to it now, and sometimes I still think that's actually pretty cool. Okay, there's one example you got to know when you talk about embedding vectors. It's the embedding vector example. It's the so-called king-queen example. So imagine you have a string or a word, king, and another string, queen. And now you want to work with those words, embeddings, like ChatGPT, etc. It's all the hype. This is actually, it's a bit oversimplified, but this is actually how it works internally, right? So you have a token or a word, king and queen, and you have an embedding for those. Let's not worry where those embeddings come from for now, right? And then you have these little logic puzzles. If I say king minus man plus woman, I mean, it says king-queen example, right? We all know what the answer will be. But it's like a logic puzzle, and we would expect it to be queen. Same goes for Paris minus France plus Italy. Anybody want to guess what the answer is? Rome, right? So we see this is like math, and we get a result, but it's math on meaning. So how does it work? Now, let's just imagine we only have 2 dimensions, because anything else is rather hard. For 3 dimensions, I'm not good enough with plotting, and 4 dimensions and higher are hard to visualize. So let's say here's our vector for man, right? This point encodes man. And then I have another vector, king, this one. So now these vectors have a distance. We could call this the concept of royalty is the distance of these 2 points, right? From this point to that point, that is royalty. Now, if we take woman and add royalty to it, if our embeddings, they need to be inherently consistent, right? It's not just one embedding, it's a system of embeddings. Then what we actually get is that we can do this puzzle. So we do king, we go here, we subtract man. See, this the same arrow as man, just turned around. We subtract man, then we add woman, and we're here. We are here at queen. So this is technically how it works. This is how we can do semantics, mathematical operations on knowledge. Yeah, it's the king-queen example. It's the example. Of course, for example, we have here the concept of gender, which we have somehow encoded here. So this is also a way where we could move around in this knowledge graph or this embedding space. So the whole space with all those tokens, now we have thousands and thousands of tokens, and they are all organized in this high dimensional space, so there's knowledge in there. This also, that way you see why we need so many dimensions. Like in 2 dimensions, it gets pretty hard to encode a million knowledge points, right? Okay. So how do we get to embeddings? Like normally our input for a neural network, like images, we encode physical information. Color, yes, there is a pixel, there's no pixel. That's physical information. Audio as well, how much is the pressure in a sound wave at a given point in time. So that is not knowledge, that's the difference between data and information, I guess. So this is data, this is not information. Embedding vectors encode semantics and meaning. So how can you imagine such an embedding vector? This is one example. So imagine this is the embedding for cat, right? Okay, just this is how I imagine it to be, and it's a good concept, but this is not literally how it works. Just we'll go to the difference later. But imagine it's like in a video game or a fantasy game where you have a character sheet for a character, like strength, stamina, etc. And here you have information about a word. So a cat is alive, so liveliness is 10. Like say it's on a scale from 0 to 10, right? The size is 3, like a logarithmic scale. It's not really tiny, but not really big. It's pretty fluffy, ferocious, etc. It's an animal, not a mineral. And now imagine you have thousands and thousands of these entries, right? So this encodes what a cat is. Now, if you pick two of those dimensions, you can actually start plotting words. Like, say we take the dimension for size and for liveliness, and then you can see that we can actually plot concepts. Like a pebble is smaller than a rock, is smaller than a mountain. They are all pretty dead. Right, rock is pretty dead. But then you have things like a virus. It's not quite alive, it's not quite dead, it certainly is pretty small. So now you can start assigning positions to concepts in a vector space. Now, the caveat here is when you have a real embedding, you can say position number 350 is fluffiness. It's not that specific. There are actually axes in this high-dimensional space where these things are aligned, and you can sometimes find them, but you cannot read directly from the vector what it actually means. Embeddings are pretty much black boxes. But it's a good way, I think, of thinking about them. So where do you get these? Like, there are dedicated models that produce embeddings. They are a bit uncool these days. They were used a lot like 5 to 10 years ago. And the most famous example being Word2Vec, Glove. There's a special bird, S-bird, which I can only recommend. It's good for text embeddings. And how do we build embeddings? So again, totally oversimplified, but Word2Vec basically works like this. You take a text. It's like self-supervised training for language models. So you remove words like the, and, etc. All the stop words you remove, and you have a sequence like bird early gets. What's the next word? Anybody want to guess? Worm. Right. So you know that worm needs to be closer to bird early and gets. And this is how it works. You repeat it again with a proper loss function, and you start with random embeddings. So for all your tokens, you initialize random embeddings, and then you repeat this process again and again and again. And this basically turns the embeddings into a structure that encodes some kind of knowledge. Pro tip: don't use OpenAI embeddings. They are frightfully expensive and actually not that good. There's a new Hugging Face model, I forgot to put it on the slide, which is way better if you want semantic embeddings. If you just work on embeddings for RAG, we will see this later or something. So there are actually tests, OpenAI embeddings, very small, very expensive, very large, very slow. Don't use them, okay? ChatGPT is brilliant, but the embeddings are mediocre. Okay. Where to get them? So what you can do, and now is the crazy part, like neural networks get input like images, anything, and they need to answer some kind of question. So what happens in a neural network is layer after layer, like every output of a layer, I can just flatten it and turn it into a vector, right? I can just turn it into a vector. And it turns out that after each layer, the neural network actually enriches the current state with information, and basically any state in a neural network is an embedding, and the deeper you get in the network, the better your embedding gets. So in many cases, if you need an embedding for a special use case and you have a network that already deals with that use case, you just take the output of the network. Generally the second to last layer. The last layer is often a classifier or regression layer. You don't want that output. You take the output before that, boom, flatten it, no matter the shape, don't care about channels, anything, just flatten it, you have a good embedding vector. Okay, this is something I actually did for another talk about clustering, just for testing, just for the laughs. I took some personal holiday pictures and I ran them through a ResNet, I think ResNet 50 or something. Just took the output vectors and clustered the vectors. And this is what you get. You actually can sort your personal pictures by topic that way. You see, here's a cluster, contains many words and stuff like that. Here's a cluster with this flower, which is actually a cactus, which I got to bloom. It's pretty hard, actually. It takes 7 years for the first flower to show. Pretty cool, that's my own one. And other flowers, and here pictures from New Zealand. So this was a typical ImageNet classifier. It was not trained to sort your holiday pictures. But the embeddings that were one layer before the output worked pretty well. And you get a nice clustering. This is, by the way, how image search works. Again, very much simplified. An image search expert could tell you weeks about how you simplify it, but this is how an image search works. So you have one image which is your query, find me similar images. make an embedding, boom, there you go. So they can be the output of a neural network or a layer of a neural network. They can be the input to a neural network. Obviously, ChatGPT doesn't understand strings because it's a neural network. So what's the input for ChatGPT? You think you're typing text. What actually happens is your text gets tokenized. The tokens are mapped to embeddings, and the embeddings are sent into ChatGPT. Then there are networks specifically designed to build good embeddings. They are great, like Espert and like the new one. I really have to update the slide. Bottleneck of an autoencoder, we get to that later. And the cool thing is sometimes embeddings are basically side products. You solve something completely different, but suddenly I get those nice embeddings so that I can do other stuff. Yeah, we'll have some more examples later. So before we continue with embeddings and how it works, I am afraid we have to repeat some math. Bear with me. I'm no math wizard either, but so you have to do these things. It's not complicated math. You can do trickier stuff. We'll keep to the basics to give a basic understanding. We introduced what a vector is. Now we have to introduce something else. It's a term you will just constantly hear, so it's better to familiarize with it. It's a scalar, or scalar in German, which we would simply just call a float, right? As a programmer, we'd say it's a single float. Technically, it can be can't be an int because it must be of a field. Okay, so it's a float. In math, it can be all other kinds of stuff like complex numbers, etc. But for now, just think of it as a float. For mathematicians, it needs to be an element of a field, which actually doesn't mean it is a number. It can a polynomial, can in certain cases be a scalar. Yeah, I think that should be right. Important thing, a vector with dimension 1 is not a scalar. So this is important to keep in mind because these are shape mismatches you will get. So there's a difference between a vector with one element and the single element. It's like a gummy bear and the difference between a bag with one gummy bear. Right, it's not the same thing. Obviously the elements of vectors are scalars. So, well, we're just dealing with floats here anyway, but you might have heard, if you sometimes see a scalar and it's something different, so you remember, okay, it can be more complex, but we're just dealing with floats here. So, how do we? Now, some other things, the basic operations on vectors we need. I already showed you addition and subtraction. I hope you remember those from school, but just to make sure, you can add a vector by simply adding the elements, and I hope this is right. Just add this one, you get the new one. So you can combine two vectors of the same size into a new vector of the same size. If you plot them as arrows, it basically means that you add this arrow and you add this arrow, you get the new arrow. Okay, that's the geometric interpretation, but basically means you just sum up the numbers. And subtraction, obviously, same thing, just with subtraction instead of addition. So king minus royalty gives you man. Vector multiplication, now here it gets interesting. There are multiple ways to multiply vectors. There's the so-called Hadamard product, which we will not look at here, it's just so you've heard it. There's the cross product, you use that a lot in 3D graphics, we don't need that either. And there are two which are interesting for us. One is multiplying a vector with a scalar, which is not the scalar product. So this is like something you get confused at the beginning. And there is the scalar product, which turns two vectors into a scalar. Okay, I can take a vector, multiply it with a scalar, get another vector, we will see that in a moment, or I can use two vectors, multiply them, and turn that into a scalar. Both of these have their uses. Let's start with multiplication with a scalar. This is what we know from school. You basically take a vector, multiply it with a number, which you get a longer vector. It's just stretches or shortens vectors. The scalar product we keep for later, okay? We need this for more advanced stuff. So with what we've learned so far, what we can do with it, we can take the length of a vector. This is a formula you will see. It's actually Satzes Pythagorean theorem. There are the Pythagoreans again, interestingly. So you can basically calculate how long a vector is. This is also what we know. This is basically the length if you apply a tape measure to it. This gives you the length. Works in many dimensions as well. It doesn't matter how many dimensions there are. It's the same principle, you just add up more numbers. Okay, so why is length so important? So in this case, size actually does matter. So length can be used to determine similarity. So how can I do this? If I have two embeddings, like if you are from Cologne, you will know that there's a special beer we like to drink in Cologne called Kölsch. And there it would have an embedding, right? If I embed many German words, I have an embedding for Kölsch. And there's an embedding for beer. Now, Kölsch is a type of beer, so we expect them to be very close. And there's cola. Cola is also a drink, but it's a non-alcoholic drink. So when we want to know if something is more a beer than something else, we can subtract the vectors. This gives us the green and the red vectors. And then we measure the length of the result of that subtraction. And if it's short, we can say, well, the original vectors were very similar because the distance between them was very short. And if the result is very long, they are dissimilar. So we can now talk about how similar two pieces of information are. So let's try this and build a one-shot classifier. So this is something, if you watched my keynote yesterday, I always tell how important data is. That doesn't change the fact that you normally don't get any, and the customer asks for a result. You ask, where's the data? Well, I thought you could do AI. Okay, so you are left. This is a true story. We actually have built classifiers with exactly one piece of data for class. So sometimes you have to do this when you're in Germany, and you kind of have to make it work. So how do you make it work? I have found this cute little data set called the Simple Dinosaur data set on Kaggle, and the question is, what kind of dinosaur is on the picture? I thought everybody likes dinosaurs, so this hopefully motivates you. Yeah, there are only 5 classes, like T-Rex type dinosaurs and ceratopsids and pteranodons and sauropods and ankylosaurs. So there are 5 types of dinosaurs, actually not species but families, but let's not get technical. So we do have 4D images, so it kind of sort of is enough to train a classifier. A bad one, but just assume we haven't, okay? We just use one image from each class, and we use the other images to test if our one-shot classifier works. One-shot because we only have one example. It's a one-shot classifier. So, because we remember, we have embeddings. So embeddings to the rescue. So what do? We initialize a pre-trained res next. It's a very useful little model I can recommend. And we just load it in Torch. And here's the important part. Of course, we need to load a pre-trained version, right? If it's not pre-trained, there is no information. It cannot produce embeddings if it hasn't been trained. So we use a pre-trained version, pre-trained on ImageNet 1K. It's a famous data set with 1,000 classes. And yeah, we just remove the last layer, because we don't want classification, right? So we replace the last layer, which is a fully connected layer, simply by a flattened layer. So we chopped off the end of the network, replaced it by a vector output. Okay, now we have our embedding building network. So how to build an embedding? I didn't put in all the code here. We load an image and put it into a tensor, right? The preprocessing of an image. And then we simply run that through our model. This is all. Look, what happened? Hello? Okay. Who knows? Okay, I'll just keep going. So basically, we have an image, and okay. Maybe you have to get out the whiteboard. Okay, there we are again. And we're going, and it's gone again. Well, you have to make do with me then, and a lot of hand waving while we try and get this fixed. So now we had an image, now we have an embedding vector, right? And now there's an input image, and we want to know which dinosaur is on it. So I have this image at the top. So which dinosaur is it? So what we basically do is we create beforehand, we have one reference image each, right? These are our reference image. And we create an embedding for each of our reference image, and we keep those embeddings. This is our model. Our model is now simply 5 vectors. And now I have an input image, and I also create an embedding for this one. And now I compare the distance of the input image with all the cached, pre-calculated embeddings. And then I get in distance, and it's very simple. The smallest distance wins. So now I can classify with that. And look here, who would have thought on the slide where I can make up the numbers myself, it works. So how did we, I actually programmed this. How did we do in practice? Print the confusion matrix. If I do only 2 classes, I think I only used the first 2, I actually get an accuracy of 82%, which is way better than guessing. If I use all 5 classes, it's 42%, which is still way better than guessing. If I have 5 classes, right, I would expect like a accuracy of 0.2 in that case. But it's not really perfect, right? But I mean, it's better than nothing if you have to do something. And still, we couldn't do this with normal programming, right? So in the 90s, that would have been crazy good, but we are not in the 90s anymore. So still, when we look at the confusion matrix, actually, we can see the problem that the first class, which I think was the ankylosaurs, they basically attract many of the other vectors. We don't know why this is yet. Let's see if we can improve this. But we can see that we get a diagonal, right? It's obviously starting to look like a real classifier, but it's not great. So now comes this long journey, which in the case of our real-world project took a few months till we actually got it figured out. There are tons and tons of tricks that you can do, and I will try and show you now the most important tricks for that. Don't expect it to work immediately. So a test like this actually is good. So if you start with that, you know, okay, in principle, we can get it to work. So the next thing is there's a process called normalization. The vectors we had before had all very different lengths. And what you can do with a vector is you normalize it. You change it so its length is 1. So if you imagine that in 2 dimensions, it means all your vectors now lie on a circle. In 3 dimensions, it's on a sphere. Actually, what your embedding vectors will be, they'll be lying on a so-called hypersphere, right? And a vector with length 1 is normalized. Not to confuse with a normal vector, which is something else, just as a warning. There's such a thing as a normal vector. Normal vectors should be normalized, but don't need to be. So now we get to our second kind of multiplication. It's the scalar product. So let's just, put it on the stack. We can normalize vectors. I will show you in a moment why this is useful. Now we do the next thing. It's the scalar product, often called the dot product. So I think it's called dot in Torch. This seems totally useless at first, but it's really useful, I promise you. You multiply 2 vectors by multiplying the first entry, adding to it the multiplication of the second entry, and so on, and the multiplication of the last entry. So you multiply element-wise, and then you add the results up, which gives you 1 number. So you can turn 2 vectors into a scalar. Now, sometimes I think I should maybe include the proof here in these talks. That would be funny, but yeah, maybe not so much. The thing is, you got to know about the dot product. It has a very, very cool property. And I promise you, this is cooler than you think. It basically, this operation here with the lines to the side means the length of a vector. So the dot product of 2 vectors is the same, is taking the length of the first vector, the length of the second vector, and multiply it by the cosine of the angle between them. So if I multiply 2 vectors in this way, the result will be this strange formula. Now remember that we have a way to make sure that the length of the vector is 1, right? So this makes the formula much easier. Much easier. Which means we get 1 times cosine alpha, which is the same as cosine alpha. So actually we can now calculate the angle between 2 vectors by just multiplying them in this way, which is super useful, you will see in a moment. Because we were talking before about distance with a tape measure, right? what you can now do is distance on a sphere. Imagine we are on a globe, right? If I want to know how far away you are, it doesn't make sense to actually drill through the Earth and take that distance. You want the distance on the globe, right? And this is the spherical distance, actually. We often don't notice it because the Earth is pretty big and the distance we're talking about are pretty small. But this is a different kind of distance. Now you take the scalar product, do some math, and at the end you can say 1 minus. The 1 minus is necessary because the cosine starts at 1. Okay, so if you imagine you have this vector here, and you go along the circle like this, the angle gets bigger and bigger and bigger. Soon the circle will be back. The cosine starts very big, then it gets smaller, then it gets big again. You just have to calculate this 1 minus here too. Basically, so you start at 0, and the bigger your angle gets, the bigger your number gets. And suddenly you have a new measure of distance, which is the distance on a sphere or a circle, which is just a two-dimensional sphere. And we can do this really, really, really fast. And this is the cool thing about the dot product. And now I changed my code. Instead of using the Euclidean distance, which is measured with a tape, measuring with a tape measure, to the spherical distance, which is normalizing everything and taking the distance. And lo and behold, we just, here for the binary case, we get a jump of 6%, which is a lot. If you remember back in the days with the first image classifiers, if you had a paper, you just improved by 6%. This is huge, right? And here it's even huger, okay? Now it starts to look pretty good. We still have this one. This is a bit weird, but all in all, this starts to get usable. Okay, we have a trick. We use a different distance. Okay, gotta look at the time. Oh man, so many slides to go. A distance isn't the same as another distance. So there are tons of distance measures, right? The most popular ones are the Euclidean distance, because this is what we count in, this is what we deal with in the real world most of the time. But there's another interesting one, for example, the Manhattan distance. If you walk through Manhattan, it doesn't help you very much. If you say, or if I were to tell you, like, this direction 150 meters, there is something, doesn't help you. You have to wait. Or you have to walk to the end of the street, around the corner, and back. And this is the Manhattan distance, where you basically just can walk on one axis at once. It's the Manhattan distance. Then there's the spherical distance, and there's literally an infinite amount of distances. So there's an infinite amount of ways to calculate distance that all make sense, and it all depends on your geometry, and which then you get philosophical. So basically, the right distance depends on the geometry of your knowledge space. Woo. So if you want to impress people over a beer, that's what you can tell them. So what you do deep learning. Yeah, well, I really have to consider the geometry of semantic spaces when I work with embeddings. Sounds nice, and it's right. Okay, ways to improve, more ways to improve the results. So first of all, I showed you use a different distance measure. What you can also do, if you have more than, like, imagine we don't have one picture per class, but maybe 3 or 4, which is an improvement. You can use many of the 2 or 3 or 4 of these references and then take the average. So if you have more than one reference image, you have multiple, taking the average of the embeddings tends to be better because you're somehow in the middle of the cluster. This makes it better. Another way is when you have multiple reference embeddings per class, don't mush them together. Keep them apart. So let's say we have 5 reference images per class. Okay, we have 5 dinosaur types, 5 per class, so we have 25 reference images. And what we now do is we calculate the distance to all those 25 images. But what we do now is we make a best of 5 vote. So we have this image. Bit hard to tell what it is, and we see that here actually, look, if we just took the best one, we'd get a wrong answer. Yeah, it's great if you can make up these numbers. And but actually, if we take the best of 5, so those are the best 5 results. So we take 25 reference vectors. We take our input vector, we multiply with all 25 of them. Then we take the 5 shortest distances, and we look which class is the most common in those. Just imagine that there are 3 images of a Tyrannosaurus Rex, right? There they are. So we actually classified this correctly. Then there are other ways to improve the results, and you will see a lot of theory about embeddings, etc. But I can tell you the best way to figure out these embeddings is just to try as much as you can. Don't overthink it, just try. So one way is just to try all the embeddings you can get your hand on and simply check which ones are better. There is no reason or rhyme, in my experience, why. So newer networks tend to be better, but we had cases where the newest networks were actually way worse. So the one-shot classifier we built for a customer doesn't even use a classifier network. It uses a totally different network, a UNet network, and we do some other crazy shit with it. And it shouldn't work, but it does. Whereas the ResNext solution doesn't work at all, which normally it should. Okay. What else? Simply try various distance measures. You simply look into your framework of choice, which one you have available. Don't write your own. You won't come up with one that is better than one that's in there out of the box. That's a waste of time. But just do some hyperparameter testing. Take 10, 20 distance measures that make sense, and just look which ones works the best. It's always interesting to see which one is right. Yeah, I mean, the obvious candidates are Euclidean, cosine, Manhattan, and then you can start and get creative if you like. Another thing that is very nice about this approach, I mean, you can do it with a classifier as well, you simply introduce a threshold. So you say, if my distance isn't below this threshold, I say it's unknown, which can improve the results a lot. This is if you have a use case where it's better to say, I don't know, instead of misclassifying. So let's say here our threshold is 1. So we have this image. Now we do not the best of 5. Now we do the simple approach again. And we see it would have 1, which is a bit sad in this case, but the threshold of 1 hasn't been reached. So we discard the result and say, well, we got a closest match, but it's not close enough. So we say we don't know. Now we have talked about images a lot because they make for better slides, but you can also build a few-shot document classifier. So all transformers and recurrent neural network architectures use these token embeddings, right? You have a document, and your document gets split into tokens. Sometimes it's a whole word, sometimes it's a part of a word. And these embeddings are the input and output of your system. So how do I build a few-shot classifier now? It works the same as with my images. I have a couple of document classes, and I have only 1, 2, 3, 4, 5 examples per class. So everything I've said about the dinosaurs before applies to documents and all kinds of text as well. So the variant A is I just use a network that's actually built for that purpose. Nice embeddings, SBIRD, for example. Or variant B, I can use any transformer, and I look at the output, and I add up all embeddings, and then I divide by their number and normalize the results, which actually works. So this gives you a document embedding. If you think about how do I get from all those, the sequence of embeddings of my transformer to a document embedding, just add them, divide by their number, normalize them, you're done. You can use embeddings as input as well. I already told you that transformer architectures do this. The question is, where do you get them from? When you, like we said, it's either the output of a specialized network or a byproduct, but how do we put embeddings into a network if we don't have another network yet that produces them? Well, we will see in a moment. You can also, and this is what I tell you now, doesn't only apply to text. Anytime you have a network that has categorical data, like the type of weather, sunny, rainy, foggy, which you can hardly put in a number. You could say that, rain is a bit less than sun, but what is windy? Like, is windy somewhere in between? I don't know. So if you have something that in a programming language would be an enum, or like a drop-down box in a front end or something, or like the type of shoe, like is a sneaker a 1 and a high heel is a 2, or is it the other way around? The very moment you think about how do I map this to numbers, this doesn't make sense, you want to use embeddings. So, but how do you get those embeddings? We will see. Magic. Okay. So what you do is you create, let's say you have like types of shoes, okay? You have 20 types of shoes. So what you do now is you take 20 embedding vectors and you fill them with noise. You don't know what they are supposed to be yet, right? You just fill them with noise. And then you say, well, my first type of shoe is a 1, and you take the first embedding vector. My other type of shoe, it's like a sandal, is a 2. You take the second. So you assign them in your programming, the integers that represent your class, you assign them to embedding vectors. And from that moment on, it's your input, right? You send that through your network. Now here comes the trick. This embedding table you treat like your other weights. So it must be a trainable parameter of your network. And then you just let the gradient run right through it. And while you're training, the embeddings will emerge automatically for you. So how does it look like? So imagine we have these. Remember those from the slide before? Now they are totally randomly initialized, right? A virus is more lively than a bacterium, a mountain. Luckily it's already a bit big, but well, a robot is bigger than a mountain, etc. So this is just random, okay? We now look at the training. While we do our training, we look how those embeddings change, and we see that the embeddings basically move to their final destination. Just by, as we know, like weights change in the neural network, bit by bit, the embeddings get moved to the right position. Okay, do we have time for autoencoders? We have 4 minutes, we can do this. First of all, I think autoencoders are totally cool. I like to include them in the slides because the audience likes them. But be warned, I find them very tough to train. They're really, really tricky to get right. They are deceptively easy to understand and really hard to put into practice. So if you start using autoencoders, it takes way longer than if you use something else. But they can be useful. So they're easy in theory, hard in practice. Imagine you have a lot of data, but it's all unlabeled. Like you're supposed to build a classifier and your customer says, well, here's the data. And you say, well, could you maybe put them in folders so I know which class it is? And they say, no, we don't have the time. Then you should actually get a student and do it for you, someone cheap. If you can't, or if it's too complex, because sometimes it requires specialized knowledge, then you're out of luck. So what you do is you build an autoencoder. An autoencoder mostly, like there are many asterisks to what I'm going to say. Okay, this is the basic case. But what you basically do is you build a network that looks like this. Big layers that get smaller until you reach the smallest layer in red here. That's called bottleneck. This is the bottleneck layer. And then the layers get bigger again. And you throw the data in at one end. I used pictures here, but could be any kind of data. And you want to construct it here. So this sounds very stupid, right? I mean, this is the easiest thing. What are you supposed to learn? I mean, there's no use in reconstructing an image you already have. But the trick is that this layer, do I have a slide for that? No. This layer is so small that it cannot pass all the pixel data into it. This is simply, what's it called, MNIST. And I think it's like roughly 400 pixels. I think it's 24 by 24. Like 400, 500 pixels. And here in this case, you only leave 16 values, like you make a really tiny bottleneck, and you cannot encode a whole image of 24 by 24 pixels in 16 floats, right? So then this network is forced to actually find structure in the data, and because we only feed it numbers, it starts to recognize shapes, etc. And it encodes these shapes here, remember? It encodes knowledge about the image. And then it creates the output. And as you can see, this is actually something I built. This is the MNIST autoencoder thing. It's pretty easy to build. And you see it's a bit blurry, but it's essentially the same number, but not quite. Okay, it's not just the blurred image, it's a reconstructed image. So what you do now is you throw away the decoder, and suddenly the output of this red thing will be your embeddings. And then you can start doing embedding things. Either you work directly with the embeddings, or you can attach a new classification layer to it, and then take that little labeled data you have and train that final classification layer. So you pre-train the autoencoder on unlabeled data. Say you have 1 million unlabeled data points, but just 500 labeled ones, right? So you pre-train the autoencoder on the 1 million unlabeled data points, and then finally at the end you fine-tune an output layer which gets as input the nice embeddings with a few hundred actually labeled instances you have. That can actually save your neck if you don't have enough data. Okay, time to talk about the next GPT hype, RAG. Who has not heard about RAG yet on LinkedIn or somewhere else? Well, that's pretty impressive. Or nobody dares to raise their hands. There's no shame in it. You don't need to know this. It's pretty cool. It is useful, but it's not so crazy game-changing as everybody does. So once you know how these embeddings work, you probably get an idea how this RAG thing works. It's called Retrieval Augmented Generation. And basically, it's used for LLMs mainly. You have the user type a query, and then you turn that query into an embedding vector. And then you have a database with, I don't know, Wikipedia articles, some wiki, company internal wiki, who knows, some text files. And you use text files that fit that query. And you take those retrieved documents and add them to your LLM. So it can look at them while answering your question. You provide additional context to your LLM, like ChatGPT should not have had access to your company internal wiki. So what do? User types a question for ChatGPT, you retrieve the documents from your own company internal wiki, add it to the query, to the prompt for ChatGPT, and have it answer questions. Works pretty nice. It's a whole science in and onto itself. It is not so super complicated and crazy and such an art as everybody does. Takes some tuning, some tricks here and there to get right. Yeah, you do that, and then you become the next hot startup, supposedly. There's a very nice tutorial here from it's a competition, but it's a very nice article. It's a company called Scriv AI. I haven't heard of them, but the post is really nice. You will get the slides later, by the way. It's part of your... you paid for the tickets, you get all the slides. This is a nice article, I liked it. It's very good it basically tells you everything you need to know. And now everybody will tell you that now you need a vector database. So first of all, if you do need a vector database, I recommend you simply use Postgres, which is a great database for decades, super tested, mega fast, and you use the free vector plugin, and suddenly you have a vector database. Or you could pay a lot of money for another vector database startup, which basically does the same thing, if that's what you like. But I will tell you a dirty trick. Unless you have more than 1 million documents, don't use a vector database. Do it in memory on a GPU. It's blindingly fast, less than 20 milliseconds. Oh yeah, and I forgot to add this because there used to be another talk, but regrettably there isn't. So on how vector databases work. So sorry, I forgot to remove that bullet point. Yeah, this is the trick, how you do it in memory. If you want to know how to do it in memory, you should have watched my keynote yesterday where I put the formula on a slide. Otherwise, you can ask me over coffee. It's really ridiculously cheap. It's 3 or 4 lines of PyTorch code, and you didn't need an in-memory database. And it's faster than any vector database, and it's faster than any vector database you could get. Yeah, that's it. Great, I think we managed in time. Again, let me repeat that. Please leave us feedback. Also, it wasn't that good because, yada, yada, yada. Also, much appreciated. Otherwise, we can improve on those talks. I slightly overdrew. But yeah, that's it. Also questions. We took a bit longer than we should. So if you need to go to the toilet, have a coffee, go ahead. I won't mind. If you have questions, shoot. Okay. Yeah, there's a question.
In order to build a RAG startup,
yeah.
That's what I'm currently doing.
Oopsie. Sorry.
My question which tech stack would you advise? Because we have Google Enterprise Search, which allows you to do something like that. You have Azure, which allows you to create a custom knowledge base for OpenAI. You've got Amazon Bedrock, who also offers stuff like that. And I'm kind of lost. I don't know which one.
Yeah. So the colleague says he's a startup that uses RAG technology. Sorry for that. I mean, it's a cool technology. If you can build great products with it, and I wish you all the best. So I wish you more success than I have with my startup, and I mean that. Yeah. And he asked what technology should he use, and you listed a couple of things: Azure, Backrod, etc. I have to, but that's maybe an age thing because I'm a very old guy. I would simply use Postgres, the vector plugin, and simply build my own structure. So this is what I would do. You'd be surprised how little there is in these products. So it is literally just make an embedding, use it as a primary key in your database, and store the data with it. What you really should pay attention to is how you create those embeddings. Look on how, I really wish I would remember the name of the model. There's a hot new model, just a few weeks or months old, and they make, it's really small, runs on a consumer hardware, and creates great document embeddings. But if you just Google that on Hugging Face, you find tons of great models. Try them out, compare them. You simply use Postgres and the free plugin and see if you have a speed problem with that. Once you get a speed problem with that, you might try out other solutions, but frankly, I don't think you need them. And it saves you a lot of money, especially if you're a poor startup. If you've got the venture capital, I don't know, use Google. Fair enough. If you got the venture capital, hit me up later and tell me how you got it. So, yeah.
So you mentioned that there was one of the solutions was to one-hot encode the items. And like, for example, if you have 20 classes, you can have 20 length bias vector and use that, for example. So we had a case when we want to include the user ID as a part of the vector in order to make it user biased. The result will be user biased, for example, for the recommendation system. And it's hard to embed it if the number of items is not discrete. So is there any solution that will recommend?
Yeah. So I always repeat these questions for the people online as well. So the question was how to include this. The gentleman did this already using embeddings and did something similar as we had on the slides. And he wanted to include what you can do with embeddings. You can actually simply add data to the vector. So you have one embedding data with information, and you can actually add another embedding data or some other information, one hot encoding on top of it. And as I understand correctly, you wanted to add a user ID to basically give it a bias. So adding the user ID would result in rather finding results that that user is already associated with. And it didn't work pretty well because the ID, I guess, was long or something like that. What I
Users are growing and you need to change the vector dimensions all the time.
and the number of users was growing. Did you one hot encode the users or?
Yeah, basically one hot encoding worked very well and every other encoding was poor.
Yeah, that makes sense. So he one hot encoded the users. So basically, if you have 100 users, you have 100 new dimension, and you encode that one. It kind of makes sense because this is say you have user 800, ID 800, and user 900. Now, if you just would add those as numbers, okay, they are close together, but why is user 800 similar to user 900? No sense. Maybe he's more similar to user 1 million. So just adding the number of the user doesn't work. And one hot encoding, of course, does work because the user then is similar to itself. And the scalar product will turn all the others into 0. But he couldn't do that because as the number of users grows, it becomes unfeasible. And what I would recommend you try is see if you have any other data of the user and try to basically build embeddings for the user, maybe on their transactions. So try other similarity. This is the next best thing I would think of, like how similar are they in certain information you have about them in their behavior, and try and basically train your own embeddings for users, maybe while they're using your system. I don't know, but it's very hard. But this is when you want to improve over one hot, you actually have to make up your own user embeddings, and you have to use some information you have about the users. So, which is basically what, yeah? And another question? Sure. No.
We are thinking about what if we will have another vector which will contain the user bias part and combine the data from the other vector database to the original one. Have you tried something like this when you try to database where you have everything biased and you can search it from there easily and just use that portion of the vector from other diseases in the main query.
No, I never did something as complicated as that. Admittedly, what I have done is using categorical data as input and provide an embedding table and have that trained with the rest and attach it. So sorry, haven't done that. But I bet there's research about it. Basically, what you want to look into research, how to remove bias in embedding spaces, which there's a lot of, and basically do the opposite. This is just, it's not meant as a joke. It's literally like there's a lot of research on it, and if you know how to remove the bias, you also know how to add it. You just have to basically change a sign somewhere. This is maybe what I would try. Any other questions? Yes, in the back.
When you said you were trying different models to get the vectors for the images, was it like domain specific or completely random?
It should be in the domain, definitely. So when you're dealing with images, simply try all the image networks, pre-trained image networks you can get your hands on. If it's audio, look at what audio networks that do something with audio, classify it, transform it. So it should, of course, be in the domain, but not in the specific user domain, maybe if that's what you're asking. So if you're just working with images, I mean, it's... Yeah, much of it is just alchemy, to be honest, and trial and error. In our specific case, we were comparing documents, and documents contain many text positions and a layout information, and the UNet we used was actually part of an OCR system. So it was better suited to think about in document layout and positioning, which was a guess. We tried it and it worked. But it's I always say those fancy ideas you have about, you know, the structure of embedding space, blah, 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 it always sounds very smart, and 9 times out of 10 it fails. It's just a hunch. So of course, if you're working in automotive and you haven't want to look at car parts or whatever, and you have another already from another project or somewhere else, you have a network that deals with industrial parts, it's likely to work better than, let's say, a general ResNet that just works on flower images. Yeah, but not necessarily. So be creative is all I can recommend. Yeah. Any other questions? Yeah.
You mentioned autoencoders,
Mm-hmm.
and that they can be a bit difficult to work with.
Yeah.
What specific problems have you had?
Yeah, so the question was that I mentioned autoencoders and what experience, and they can be a bit tricky. That's I say you phrased it very mildly. They are like really annoying to work with. What we already did with that. So first of all, I made a talk about autoencoders, so I had to test them. So I tested them on the usual toy projects. Well, but we actually used them on real data once, where we had industrial data, like terabytes of it, but no annotations. And there we actually trained terabytes on data on a convolutional autoencoder, which kind of sort of worked and gave us, well, we have a good hunch that it will continue to work well once we get labels. So afterwards, what we simply did was we did a clustering, high-dimensional clustering of the embedding vectors, and we saw that the measurement, it was ultrasonic measurement results, that the measurement results that were close together in one cluster had similar patterns and were just similar. Which hopes that one day when we get the labels, it's been 3 years now, we are still waiting, that maybe the classifier will become better. So this is where we actually used in an actual project, and as you said, it was really hard to work. It was hard to get them to converge. It was really hard to put them together because there are not so many out-of-the-box implementations like in other networks. Yeah. So this is where we did it for where we have tons of measurement data and just no labels. And the preliminary tests were positive. That's all I can say. Yes. No more questions? Great. Let's get coffee. If you have any other questions, I'm just walking around here. Feel free to chat me up. I always like to talk about this stuff. See you around.